All right. Hopefully we didn't miss too much. Okay. All right. Where was I? Oh yeah, simulations versus calculations. So calculations will be theoretical. Simulation, something you could perform on a computer, and so you could compare theoretical calculations versus computer simulations, software simulations. Note this: lowercase m is milli, mu is micro. Okay, so milliseconds, microseconds, noted with lowercase m and Greek letter mu. All right, reasonable numbers. What are reasonable numbers? What do you think it means? If your source is 10 volts and you obtain a result of 15 volts anywhere in the circuit, that's not possible. That's unreasonable. So that's a quick verification and check, right? If your source, or let's say there are multiple sources in the circuit, but the highest value for any of the sources is 10 volts, no voltage in a circuit anywhere in the circuit could be higher than that number. Okay. That's a good question. I will answer that in just a second. In a minute, actually. If source is 10 volts, no voltage in the circuit can be greater than 10 volts. All right. So the question being asked was, what about op amps? Specifically, I'm assuming running an op amp as an amplifier, right? So let's say we have a amplifier, any kind of amplifier, let's say, not just an op amp. So we have an amplifier, and this is actually an important concept. Okay, so you have V in and we have V out. Let's say the gain AV is equal to 10. Sorry, dimensionless. So gain of the system is 10. Now if V in just based on these facts, let's write out V out. If V in is 1 volt, what is V out? If it's 10 volts, 100, that's 100 volts, 1000 volts, right? But remember we few slides ago talked about AC and DC, right? So most of the electronic devices that we look at and the applications that we look at have both AC as well as DC. An amplifier, and again, this is a very important question. This is an important concept. An amplifier takes an AC signal and imparts it some energy, strengthens it. It could strengthen the voltage, it could strengthen the current, or it could strengthen both voltage and current. So we have both voltage amplifiers, current amplifiers, and power amplifiers. Okay, that energy does not come from thin air. That energy comes from a DC power source. So for an op amp, or for any amplifier for that matter, to work, we need a DC power source. And hence we have a mix of both DC as well as AC. So a simple or a simplistic representation or example would be an amplifier is DC plus AC. Actually, I should say AC plus DC. Again, this is a very simplistic presentation. You have AC signals that are very small, right? Perhaps millivolt range. And then you have a DC, and let's say this is 10 volts DC, and this is millivolts. What does an amplifier do? An amplifier takes that DC waveform or the energy from the DC waveform and imparts it to that AC waveform. And so the result is something like this, depending on the design of the amplifier system. Okay. Again, this is a very important concept, so I'm glad the question was asked. This is what we'll be doing in the labs, and this is the theory that you'll be learning, right? So the energy does not just appear from thin air. It is capped. It is capped or is constrained by the DC power supply that we are providing system. Okay. I also like to state, the amplifier takes the DC waveform and gives it the shape of the AC waveform. That's another way of stating it. All right, let's take a pause. Let me know if you have any other questions. There is also an additional exception to this statement, and I will talk about it in just a little bit. Any other questions? Oh, 352. All right. Okay. So reasonable limits, reasonable numbers mean that our output should be within our supply voltage limits. Power supply voltage refers to the DC power supply. Okay. Then there are AC signal limits, right? There are reasonable numbers that apply to both DC as well as AC. Current range, if your current is coming out to be like, I don't know, 150 amps or something, or even 10 amps for a small system, that is also not realistic. You know, if your circuit is working or operating in microamps and milliamps, then if you obtain amps as a result, that's also not reasonable. Okay. Calculated component values could be in kilo ohms, could be in microamps, microfarads, millihenries. And so those all come under the umbrella of reasonable numbers. So let me talk about the exception to this. And this is something we'll look at in clampers, in clamper circuits. In the circuit series of classes, we learned about energy storage devices like inductors and capacitors, right? So inductors and capacitors receive energy from the source, they store it, and they release it back into the circuit at a later point in time. That later point in time could be microseconds, could be milliseconds, could be a few seconds, who knows, right? Depends on the design of the circuit and size of the capacitor or the inductor. So in clamper circuits, any circuit for that matter, if you have a capacitor, that capacitor charges up, you apply an AC signal, let's say. So in one direction, it charges up. Now it's storing this energy. Now the circuit is configured in such a way that this stored energy appears in series with a negative half cycle. Then your resulting output voltage would be larger than your input supply voltage. Again, if you have storage element in your circuit, the stored energy in this element could combine with the source and produce larger values. Okay. That is one example of an exception. A capacitor or inductor stores that energy, and then in a different half cycle, that stored energy could combine with the source, and then you could have voltages or currents that are larger than intended. So that's an exception. But other than clamper circuits, we are not going to encounter those. Okay. So for the most part, be cognizant or be aware of what a reasonable number should be for your circuit. If you don't have a capacitor or inductor in a circuit, then there's no reason why your output or any voltage or any current in a circuit be larger than the source. All right. Okay. Let's see. What else is there? Oh yeah, circuit analysis. Again, just a refresh, just making sure everybody is on the same page. In circuit analysis, you learned about Ohm's law, KCL, KVL, right? All of circuit analysis is based on these three principles and laws. That's it. These are the only three things that you need to know. All of circuit analysis, node voltage analysis, mesh current analysis, superposition, resistive analysis, current division, voltage division, everything is based on these three. Entire electrical engineering circuit analysis is based on these three principles. If you master these three, you can learn the rest. Everything else is derived from these three. Okay. So Ohm's law is V equals IR. KVL and KCL are based on law of conservation of energy. KCL is current law, meaning if you have the sum of currents at a node is equal to 0. KVL states that the sum of voltages around a loop is equal to 0. KCL is a little bit easier to visualize. KVL, I mean, I know what it is. I know how to apply it. I can generate the mathematical equations. But somewhere in the back of my mind, I still can't really grasp on how beautiful it is that it always sums up to 0. No matter what kind of circuit it is, any electrical loop you take anywhere, sum of voltages will always be 0. And it's just, it still to this day, it boggles my mind, right? So again, Ohm's law is V equals IR. Voltage and current are directly proportional. The constant of proportionality is the resistance. That's what Ohm's law is. KVL, sum of voltages is 0. KCL, sum of currents is 0. Well, sum in the sense, if you add up the currents at a junction or a node, well, some are entering and some are leaving. Typically, the way I write my KCL expressions is I have an equal to sign, and I would say all currents entering on the left side, and all currents leaving on the right side. And I have my KCL expression. As easy as that. And you're all EEs for quite a few years. You have learned this in physics. You'll learn this in circuit analysis. So you would have your preferred method of applying KVL and KCL. So you stick to that and you just continue doing and applying your laws as it is. All right, so we'll end class here today, and we'll pick up here again on tomorrow. Just a few more examples like voltage division, current division, and then Thevenin and Norton equivalent circuits. And then we'll wrap up chapter 1 on Friday. Hey, homework has been posted, so please keep up with the homework. It's already available at your end. If you have any questions, reach out to me. All right. Next class.